Hi everyone, and welcome to episode number 3 of the Amiga game development series that I'm doing. Super duper pleased with the response that I've had so far from everybody in the community, so I thought I'd best get episode number 3 done pretty quickly to keep the momentum going. So some changes that I've made since episode number 2 is that somebody suggested that the audio wasn't actually quite that good in the previous 2 episodes, so they suggested I get a mic, and which I did, and I got one of these V-Fine mics, I think that's how you pronounce them, and yeah, it's pretty good. It sounds a bit well, it sounds a lot better actually than what I was using, so I'm quite over the moon. Let us know what you think in the comments, and yeah, and hopefully it'll sound a lot better. The other thing that I've getting, which I've been really meaning to do for quite a while now, is actually get a green screen. I was quite aware when I've done Amiga build stream that you know, people could kind of see the back wall in the living room where I actually sit and do a lot of the coding that I do, and you know, people could actually see kind of inside my house and through parts into the kitchen and things like that. So I thought I'd get a green screen, because it does actually have multiple uses as well. What I figured was that I could use it for doing lots of like family stuff with my little boy, and kind of putting them into scenes and making some cool scenes where we take photographs and things like that. So yeah, different. So yeah, a little bit different for us. And it is a mobile one, so I can just put it straight down and kind of put it in the conservatory real fast. But yeah, onto some other things as well. I actually added an SSL certificate to the AmigaGameDev.com website as well. So if Google pops up with any error, you know, with any kind of security warnings or anything like that, you know, that should now go away. I guess really it's on to episode number 3, which this one's going to actually cover loops in assembler, memory, and a simple handler. And I'll kind of wait and go through, and you'll see what I mean by that title. So yeah, we're going to get it underway, and hopefully you'll understand what I'm saying, and you'll find out some interesting things. So this is what we're going to cover. Episode number 2, quick recap, loops and conditions. We're going to do some bit shifting. We're going to take a very quick look at the Amiga's memory map. I'm going to cover the Amiga memory map in a lot more detail later on, in later episodes, because it really does deserve a bit of attention. We're going to look at declaring some simple blocks of memory. This isn't allocating memory, this is just declaring some blocks of memory in assembler, some very small blocks. We're going to look at some more assembler instructions like load effective address, and we're also going to look at more move instruction, well, more about what the move instruction can do. We're going to be looking at copying a block of RAM, and we're going to also take a bit of a look at how a classic game might look as far as how it's handling some of its sprites. A really simple example which I'm going to give, which hopefully should kind of set your mind in motion about how games kind of handle objects and things like that. So yeah, that's what we're going to be covering today. So a quick recap of episode number 2. This is what we covered. Very important, the numbering systems. Base 10, as I've mentioned, is, you know, normally when you go through primary school, the teachers will teach you how to count from 1 to 10 or 0 to 9, somebody mentioned. But computers typically deal in base 2, which is binary, 0s and 1s, or when you're coding, generally a bit easier is base 16, which is hexadecimal. We talked a bit about bits, bytes, words, long words. So bits are, as I mentioned, binary, 0 or 1. Bytes, you've got 8 bits in a byte. A word is 16 bits or 2 bytes. And long words, you've got 32 bits or 4 bytes or 2 words. We talked about the more significant bits and the least significant bits and what those typically mean. We looked at some Boolean logic as well. So really, you know, you can't really get along in programming anything really without kind of understanding these concepts. So and, or, not, and XOR we looked at, and we looked at a bit more focus on the 68,000 CPU, and we looked at how many data registers got, which is 8, the address registers. We looked at the stack pointers very briefly, but we did take a real deep dive into the status register, which is really important. And what we looked at there was how the negative flag gets set, and we were testing for that, and how the 0 flag gets set, and using the branch if equal to hook into that. We looked at the overflow flag. We looked at the extend and carry flags as well, which the extend and carry flags are very similar, but just affected by different instructions. We looked at a really common concept that I use called there are termed tri-states, which is to say, well, is the result of something either 0, negative, or neither of those, of which the state is something else. And we were able to create 3 branch conditions based on that. And we took a basic look at Monarm as well. So, you know, just kind of easing our way into Monarm. We're going to cover it a bit more today. So onward we go. So loops and conditions, very important. Typically, if you do any programming language, you'll come across a for loop. And in this for loop here, what we're doing is simply going from, we're setting I to equal 0, and we're counting up through to 31. So we're going 0 through to 31, so 32 iterations. And in these braces here, we're saying do something with I. So if I is, you know, if I is 5, when, you know, I might do some code based on that integer. So we take an I as an integer. Or you might do it like this. You might use something called a while loop, where in this instance we're actually counting down. So we're saying, right, we set I to equal 31, and then we're going to count down to 0. And that's what's happening here. So we set I to 31, and we do while I is greater than 0. And in these braces here, we say do something with I, and I then gets decremented or decreased each time this code section runs down to 0, and then it breaks out and continues on. So how would you do that in assembler? Well, this is what it looks like. So first, the for loop. This is just one way you could do it. Really simple, and I've commented the code. So first of all, we do a move of a word into of 0 into D0. That is setting the I to equal 0 here. And then we've got a compare to say, has I reached 31 yet? And if it has, then we're going to be finished. So if I has reached 31, then we're kind of going to be in this, outside of these braces here. However, if I is not equal to 31, we're just going to add 1 to DO, which is to increase I. And then we're going to just keep looping around. That's what we're going to be doing. And we've got here the do something, so we're going to be do something in typical fashion here. We might do something with DO, which is actually the I integer. So that's how we do the for loop. What about the while loop? Well, the while loop in assembler is actually a lot easier, and it's typically why they're used a bit more, I think. So similar sort of thing. It starts off with, we move 31 into DO, which is setting I to 31, as we're seeing at the top here. But then we move into a loop, and we come across an instruction that I don't believe we've covered before, and this is decrement branch if false. And what it does is it says, right, whatever the value is in DO, if it isn't negative, I'm going to loop back to this code here. Okay, so what it'll do is it'll say, is DO negative? And it'll say, right, if it's not, it's going to subtract 1 from DO and loop back to wherever we set this branch to. So which is a local label called .loop. So what will happen is this do something code that's between the loop and the DBF will get executed 32 times, including the 0, and when it gets to minus, it will come out and drop in here. And that's pretty much all there is to that, really. So we're going to take a look at some examples in Monarm and get used to doing Monarm a bit more. So we'll take a look at the for loop first, and I've got some stuff set up in the virtual machine with a bit of luck. Indeed we do. So this is the for loop example which I gave in the screenshots. So what we're going to do is we're just going to save and compile this. So Shift F10, and we're going to do a Shift F12. And here we go. So we've got to set DO to 0. That's what the clear flag. That's what the clear instruction does. Is the assembler will, due to optimizations, might make changes to certain instructions, but typically they will always do the same sort of thing. So as you can see there, we set D0 to 0, and we're comparing D0 to 31. Now I know in hexadecimal, that 1F in hexadecimal is 31. Now to check that, you can press O, and if you type 1F, it will tell you that hexadecimal 1F is 31 in decimal. Okay, so we're going to check, is DO equal to 1F? If it is, then we're going to branch out and come down to here. Now, no, it's not. So we're just going to add 1 to DO. And it's going to keep doing it and keep doing it until it reaches 31. Now, it's all well and good that, you know, I could sit here for, you know, and trace for, you know, until it reaches 31, but what happens if that was 31,000? I don't want to be kind of keep going and tracing until DO reaches 31. That would take me an absolute age. So this is where breakpoints comes in really handy. So what we can see here is that if I were when the condition's true for DO equaling 31, we're going to take this branch here to this memory address C26FC4, which, if we look in the code, is actually this done flag here. Okay, so what we can do, we can just scroll down, and as we can see, the done flag is at NOP, and if we notice, that address is C26FC4. C26FC4. And if we come down and just focus on there, right at the top, so it has to be at the top, and we say Control B to set a breakpoint, so that little in braces 1 there, in the square brackets 1, means that's your first breakpoint that's set. Okay, now if I just press Control R to run the code, notice how it hit the breakpoint and then it removed the breakpoint. So that's fantastic, because what we can also see as well is that DO actually reached 1F, which is 31. Great, so that's the for loop actually finished, and then what happens is it'll exit, and that's job done. Okay, so we'll just load the while loop now. So let me, I think I had that set up, so we're just going to revert a snapshot, and we'll go. These snapshots take a little bit of time to kind of load up, take a few seconds. Okay, cool. So, and there we go. So what we're going to do is we're just going to press Shift F10 and Shift F12. So remember, this is the while loop, so we're going to count down this time, and remember that DBF instruction will actually do a decrement if false. So we're just going to take a look at that. Okay, cool. So similar to what we did before, we've got to set the DO, set the data register 0 to 31, which is 1F. And notice this DBF DO, and what it does is it simply just goes back to itself. So C26FBC. Now what I'm going to actually do here is I'm just going to keep tracing. As you can see, DO is actually just decrementing down all the way down until it reaches negative. Now notice it still worked on 0, but once it's done 0 and hit -1, which is negative, it is then dropped out into the next instruction. Cool. And it is that simple. Now in our code, when we have say do something here, we could say, okay, you know, we could have it do anything. We could say move.w do, d1, and then do something with d1, etc, etc. That's just a quick example of showing you how the dbf instruction works and loops. So a couple of ways to do that, using the compare instruction and counting upwards, or using the dbf instruction in similar to a while loop and counting down. Okay, so just gonna go on to the next one. So what we're going to do now is take a little look at bit shifting, which is very, very common in assembler with what we do. So this is a bit of just a refresher table, which was from episode number 2, and what we've got is we've got the bit set here of a byte, and we've got bit 7 set, which is the most significant bit, which adds up to 128, and then we've got bit 5 set, which is 32, and bit 3, and bit 1, and bit 0. So that in decimal adds up to 171, or hexadecimal AB. Okay, now what tends to happen is that you tend to need to shift kind of bytes or, you know, nibbles around quite a lot to do general things, and the way you do that is through a technique called bit shifting. And to give you an example, that is the same table above, but all of the bits are actually shifted by one to the left. So you'll see here that bit 0 has been moved to 1, as you can see there, and bit 1 has been moved to 2, and bit 2 has been moved to 3, and bit 3 has been moved to 4, and so forth and so forth. So now the byte, if you calculate everything up, in decimal it's 64, 16, 4 and 2, which is 86, or in hexadecimal that is actually 56. Okay, so we're just going to take a look at a few examples. So this is an example of using the LSL instruction, so that is logic shift left. And what you do is you say logic shift left, and you give it the size of the amount of data that you want to shift. So in this case, it's a 16-bit data width, and we want to shift it left by 1. Okay, so we're going to take all the bits like the example we had previously, and we're going to just shift them across to 1. And then the next instruction is LSR, which is logic shift right, and all we're going to do is we're just going to shift them back right again. Now, an interesting thing that happens when you start shifting bits left and right, what you're essentially doing is you're actually multiplying the bits by the power of 2. So if you have 1 as a value and you shift it left by 1, you're actually doubling the number. If you then shift the bits by 1 again, you're then doubling the number again, and if you shift them again, you're doubling them again, and so forth. And the same works the other way. If you're shifting them right, you're going to divide the numbers by to the power of 2. And here's a few more examples here, so probably more real world these, I think. And we're going to look at these as well in Monam. And here we're going to move 1, 2, 3, 4, set DO to equal 1, 2, 3, 4. And we're going to do a logic shift left, this time on a byte size, and we're going to shift it by 4, and the comments that I've put in there is multiply byte and DO by 16. So as I said, 4 to the power of 2 is actually 16. We're going to look at moving another word in there, beef, which is actually a valid hexadecimal number, and then we're going to divide that by 2 to the power of 2, which is 4. And then we're going to look at another instruction called rotate right and rotate left. 2 instructions, and we're going to see how those are affected. And remember when I said in episode 2 that 4 bits is a nibble and 8 bits is in a byte, So I've got a typo there, rotate nibble left, that should be 4. So yeah, we'll look at that. Okay, quick example as I mentioned, and hopefully I should have things up and running in a snapshot. And let me see. And I'm on the Peroni tonight, but I'm not sure whether you can see it behind me green screen. Kind of, probably just see the label. So here we go. We're going to play around with these instructions here, and just go through the examples. And so I've done Shift F10 there and Shift F11. And let's load things up. Okay, so what we're going to do is we're just going to set DO to equal to the value of 1, and we're just going to prove what I was saying about, you know, doubling the number. So logic shift left will double the number, and as you can see, it's doubled it to 2. And if we quick look at our slide again, we'll see why that is. If you look at bit 1 or bit 0 here, which is 1, that would be the value of 1. And if that's shifted to the left by 1, you'll see that the value then becomes 2. Pretty straightforward. And then what happens if we shift it back again to the right? Well, sure enough, there you go, it becomes 1. And so we're going to look at the next set now and see what happens here. So here we're going to set DO to 1234, which is a valid hexadecimal number. This time we're just going to work on the byte. So when we've got 1234, the logic shift left is only going to operate on the 3 and the 4 here. See that? There's just 3 and the 4 in the lower byte. And watch what happens. You'll see that by shifting 4, it is actually just moved the 4 into the next nibble. Okay? See how it's done that? It's just moved the 4 into the next nibble, and where the 3 was, that has been shifted out and discarded, and you won't get that back. So now what we're going to do is work on a byte, on a word instead of a byte. And this time, you see, we've got the same instruction, but it is working on a word size. So we're just going to shift it across, and what we'll see here is the B that gets discarded, and we'll see the E and the F move along to what we know. This is actually a shift right. I do apologise. This is actually going to move the B and the E across to the right. And you see that? And look what it's brought into the highest nibble of the word. It's just shifted in 0 data, so there's no bytes. But the key point of this is that you can move the nibbles around just by shifting by 4 bits at a time. So another quick example, what sometimes you might want to do. So we're going to set D0 to 6789. And remember, this is the rotate right instruction and rotate left instruction, and they're going to both be working on word data sizes. So what we're going to do is we're going to do a rotate right by 1 nibble, which is 4 bits. And as you can see what it's done there, it's shifted it right, but it's the point of the rotate is that the bits that were shifted out to the right have been shifted back into the left. So now you have this 9678, so it's rotated round. And similarly for the rotate left, what we should see is we'll see the bytes move around to 2 nibbles. And there you go. We have 7, 8, 9 and 6. So the bits are just shifting around in the size of the data, in the size of the word that you're operating on, which is a 16-bit word value, and you can move them around in any position that you need to, which might not seem relevant at the minute, but it will be later on. Okay, I hope that was clear. And what we're going to do now is we're going to actually look at something a bit Amiga specific. Now, the Amiga memory map, which is a bit important because we're going to be starting to look at this, looks a little like this. Now, when I say Amiga memory map, I'm talking about stock Amigas. Amigas that back in the day you bought them and they came as stock machines, and you know that it's just the amount of RAM that they would typically have. Now, when I've got memory ranges here, I'm going to show you this in one arm shortly. These are where the amounts of RAM are actually allocated in memory. So when you bought an Amiga A500, it came with 512 kilobytes of chip RAM, and we'll talk about different types of RAM later as well. And if you wanted to access that chip RAM, you would do it in the memory ranges between 0 and 7FFFF, which if you do a hexadecimal lookup to decimal, you'll see that 7FFFF equals 512 kilobytes. If you bought an A600 machine which had the ECS chipset, I believe that came with 1 meg of chip RAM. And so what Commodore did was that they had the 512 KB of chip RAM in memory ranges 0 to 7FFFF, and they added some extra chip RAM between 80,000 and FFFF. That was typically that. So you had an entire 1 meg range of chip RAM right there. And again, when they released the A1200 machines, they came with 2 meg of chip RAM. And so what they did was they had the stock RAM that the A500 and A600 had, and they just added, and if you look and do your calculation, they had this extra RAM here, which is 1 meg, making the stock machines 2 megabytes of RAM. Now these here, which I'm not really going to cover yet in any great detail, I'm just going to talk about them I should say, is kind of the hardware mapped registers that allow the Amiga to do things and allow you as the programmer to actually communicate with the Amiga. So the Amiga has 2 of these chips, these complex interface adapter chips, and they control things like your keyboard. One of them controls the keyboard, one controls the disk drive, keyboard, mouse movements, light pens, trying to think what else. A whole host of things that these 2 chips actually do. In fact, you know, if you ever have a fault with one of your Amigas and maybe the keyboard doesn't work, it's a possibility that one of the tracks or one of these chips has actually been damaged, or you know the floppy drive doesn't work. You know, it's possibly a cause that one of these chips is actually broke. But you know, this isn't a hardware thing. This isn't a hardware video. You know, I'm sure there's plenty of other videos that go into that. If you have some fast RAM, which in these examples we actually do, you'll notice that the memory range of the program counter kind of lands in this range here. So if you added fast RAM or into the underside of an A500, you would typically get that RAM added into here, and you'll see it land, I think it was about C80,000 or something like that, where it actually allocates that extra RAM. Now these hardware chip register addresses here we will come on to and we will delve into in great detail later on, but typically if you want nice things to happen on the Amiga, you do a lot of things with the hardware registers that are here. We'll be covering those in great detail a bit later on. And then what you have is you have the actual ROM of the Amiga. which is mapped into this these address locations here. You typically don't have anything to do with them, just leave them alone. Whatever you do, do not jump directly into ROM. Things will just not end well for you if you do that. So we're going to again take another look at a quick example of what I'm talking about, just at these memory ranges here, just to get you more familiar with MonArm. So we're just going to keep the session that we had, and just to verify a couple of things. So you see I mentioned there about the fast RAM. Now this does have fast RAM enabled. If I take a look, you'll notice there that I have 1 meg of fast RAM. Well, it says slow, it's actually slow RAM, as is in WinUAE. But that is the use of the expansion slot. And as you can see here, the Amiga is loaded and actually used that RAM, which is why you get this address here. The C, it begins with a C, which is totally fine. But we're just going to look, given that this is an A1200, we're going to look at the memory ranges. So if we want to see what's at address 0, we can just press M and then type 0, and we see, there we go. And I'm just paging down, shifting down arrow and shifting up arrow, and we can go up and down RAM. And then if I press M and then type 80,000, there's nothing in RAM at these addresses, so that's just all 0. Maybe if we look at 100,000, yeah, so that is just beyond the ECS RAM and into AGA RAM, the AGA chip RAM. That is what that is there. And as you can see, none of it has actually got anything in it, because we haven't actually loaded anything or doing anything with this RAM. It's just available as a resource. Now if you try to go to the actual hardware addresses, you'll be a bit disappointed, because it'll just say stars or have asterisks as they are here, and that is typically because the limitations of MonArm typically don't allow us to actually read those addresses, but there is ways to do it, and we'll be looking at it later on, because WinUAE has a very powerful debugger, and it is entirely possible to use WinUAE, which I'm just going to show you here with Shift F12. And if we want to see what's in some of those registers, I believe E is the command, and it is, what we're actually seeing there is the values of these chip registers here. But like I say, we will come on to that later on. Okay, on with the show. Now with this one, I just want to show you about declaring some memory and some very simple assembler directives that can be used to help you. Now this is a new instruction called DC, declare, and what I'm doing here is I'm declaring different types of memory in my program. So I'm saying declare a byte, and I want that byte to be 0, the value of the byte to be 0. And here what I'm saying is I'm declaring a string of bytes, and I'm saying hello world, and then I'm got a comma there, and I'm ending it with a 0. That is typically called a null terminated string. Or I'm declaring a byte there with 50, or I'm declaring a 16-bit value, which is a word, with the value of $100, which is 256. Or I'm declaring a long word here, which is has the value of dead beef, which is a valid hexadecimal number. Or what you can do is you can use the declare a segment. I believe that's what the S is for, declare segment. And what you do is you can declare a set of value, an actual memory block. So you can say, right, I want to declare a segment of bytes, and I want 30 of them. So what you will get is you'll get a space of 30 bytes. Or if you want some words, you can have 30 words, so that would give you 60 bytes, and if they're long words, because that's double again, you'll get 120 bytes. This is a nice directive here which I use a lot, and this comes with the VASM assembler or dev pack as you had it if you had it back in the day, and it's this one here, this rept, and it stands for repeat. And what you do is you want to say, it's whenever you want to kind of repeat some instructions or you want to repeat declaration of bytes, what you can do is you can say, all right, if I want these instructions in this block repeated any number of times, you can just say rept and then give it the number of times you want them to be repeated. And at the end of the block, you just say end repeat with the end or directive there. And in between, I'm saying declare 10 times dc.b declare byte, and I'm saying rec for record. And interestingly, what I'm doing after that is declaring another byte, and I'm saying rept n, which is the number. So this is the counter, which is actually going to be in there. So I'm going to actually put these examples in now and show you what they actually do. So let's take a quick look. I'm going to just do this, and I'm going to say, right, declare a byte 0, and I'm going to declare a string hello world, and I'm going to declare a word which is what was $100, I believe, and then I'm going to declare a long word which is dead beef. There you go. That's the first example. Okay, we're going to look and see what that. Take a look and see what that looks like in memory. So what we've got to do is we've got to press tab and move across to the memory part here, and as we can see, if I can just move this down, yeah, oh, no we can't, what have I done there? Yeah, there we go. So what we can see here is that the dc.b0 is actually this byte here. Get the mouse, and there you go. And then what we've got is we've got hello world as a string, and we've seen the ASCII representation of that in the following bytes here. So these are the hexadecimal bytes of hello world, and then we've got the value of $100, and that value is there, as you can see, 100, and then you have the value dead beef, all there. Now, a really important thing which I want to bring to your attention is, and I've purposefully done this, there comes a time when you really don't want your long word values such as dead beef to be what I would call on odd word boundaries. Okay, that means that if you look at the value of dead beef, or you look at the word value of 100, it's actually starting on an odd address. You notice that if you look here, we've got this particular 0 here starts at the even address, and then we've got the 01 which starts at C26FC5. That is actually really bad if you want to try and do anything with that value from a performance point of view. So what we need to do is we kind of need to what's called even things out, and the way you do that is quite simple, because after you declare any bytes, what you can see is that you can just use the even directive, and what the assembler will do is it will ensure that this value here, this word value, will be put on an even boundary. So I'm just going to compile that up and run it again, and I'm going to show you what I mean. So yet again, let's take a look, and you will now notice that if we look a bit further down, we'll see that we've got an extra padded 0 here, and the $100 starts now on an even byte. As we said, that is what this even does here. It makes sure that the next value starts on an even memory address. And you can see here that you have dead beef, which is stored there, which is exactly what we want. So it just kind of get in the habit when you're working with bytes that you will need to put this even directive in there to make sure that things are even out. Otherwise, you'll run into all sorts of different problems. Okay, so what we're going to do now is just look at the rept directive. So as I mentioned, you can use rept, and we're going to say 10 iterations, end repeat here. And the example that I gave was the declare, and we're just going to say DC and rept n. So what we're going to do is this is going to say repeat this 10 times. In the first 3 bytes of each record, which is 4 bytes in length, the first three is always going to see a rec, but then we're going to be counting 1 through to 10. So let's have a look at this. Just see what it says. And there you have it. If you look, you will see that in memory you have, as I've mentioned, 10 iterations of rec. But if you look at the byte that comes after the C, we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It is counted up using the rept n directive, which comes in very, very handy when you're doing things like tables. Really, really handy. So just keep that in mind and in your back pocket for later when we come onto it. Okay. So with that done, we can look at some more things now. And we're now going to look at an instruction called leah, which is load effective address. And what leah does is that it makes it, if you remember the address registers that the CPU has is, you know, you've got A0 through to A7. What leah does is it says, right, point one of those address registers to an area of RAM. And the area of RAM could be anything. It could be pointing at a global label, a local label, it could be pointing at anything. But it becomes very important when you need to actually do things with things in RAM, because typically all a game is just moving things around in RAM and manipulating RAM at any given time. So here's the example, and what we're doing is we're just saying leah source into A0, and source simply has dc.b, a string in RAM, and it is that simple. And if you were to look in Monarm, which I'm probably going to show you in a sec, you will see that if you trace the leah instruction, it will show that A0 now points to a string in RAM. It's the memory address where that string belongs. I'm just going to quickly do this just for completeness. So I'm just going to say source dc.b, I love Amiga, and get used to doing that even directive, and we do leah source, A0, and we'll just compile it up. So you'll see at the minute A0 is pointing to a particular address. We don't know exactly what it is, we don't really care. But if we set our window address here and say source, we'll see that the string that's in RAM, its address is C26FBC, and what we typically want to happen is we want A0 to point to C26FBC, And sure enough, that's what load effective address does. So if we trace that, we will see that A0 points to C26 FBC now, and you can see there it's give us a bit of a summary of what's there. I love Amiga in the string, and those are the hexadecimal bytes there. That's pointing at that address. Pretty straightforward, I think. Okay. So we're going to look at a bit more of a deep dive into the move instruction and cover what that can do. Previously we've just looked at moving a value into a data register or an address register, but what if we want to actually manipulate the memory behind or that is pointed at to by an address register? Well, that's actually called dereferencing. So this is an example here of what the move instruction can do, and we've got two address registers here, which, as the term used is are being dereferenced. It is looking at or manipulating the memory, the bytes that are pointed to by that address register. And what we're saying is we want to move whatever's pointed at by A0. We want to move that byte into the value that's pointed at to A1. And what the pluses do, or conversely you can also have minuses before these, you say once that byte is being moved, we're then going to add a byte value, which is 1, to the address register. Now if we were moving a word, that would be 2, it would add to A0 and A1, or if it was a long word, so a move.l, it would add 4 bytes to it. And like I say, if it was a minus that you had here, which I'm going to show you an example, it would decrease it by 4 or 2 or 1. So just do what I've written here: move a byte from A0 dereference to A1, move a byte from A0 dereference to A1 dereference, then increment address registers. That's it in a nutshell. And I've got a bit of an example here as well how to do it. So I'm just going to really quickly run through some of these examples, and just to show you what I mean. Let me get this right. Yeah, so I'm just going to say, right, source, I'm going to say, right, dc.b, I am copying this RAM, even and dest. I'm just going to declare a memory segment of 30 bytes. I'm just doing even again. Like I say, we've just learned about layer load effective address, and we want to say source, comma A0, load effective address, dest into the A1 register. And what we're going to do is we're just going to say, right, move.b, which is move byte, from A0 into A1. Okay, and watch what this does. And we compile it up. So let's bring this into view, and so we're going to point A0 and A1 to our memory, and A0 points to our string, and what we're essentially going to do is have A1, which points to our empty block of 30 bytes, which is here at C369F4, and we're going to do this move.b, move.byte, from A0 dereference to A1 dereference. So what it's going to do, it's going to move this I into the value that's pointed at by A1. So the value that's pointed at by A1 is this C369F4, which I've got focused here, C369F4. And what you should see is, you see this I move into this byte here. You'll actually see the I appear on the ASCII side here. So when I trace that, now one thing to watch is watch what the values of A0 and A1 do. Currently they're at, if you just think of, they're at 9DA and 9F0 if we take the last 3 bytes. Watch what happens to them. And what's happened is they've both been incremented by 1. So previously they were 9DA and 9F0. They've now gone to 9DB and 9F1. And you'll also see that the I has been moved into the destination block of 30 bytes. So this is a way of how we can start moving bytes around in RAM. And I'm just going to give an example of Word as well. But what I'm going to do is I'm just going to say I'm not going to increment A0. What I'm going to do is I'm just going to increment A1 and just see what happens. And I encourage you to look up these instructions as well. There's some really good resources, and just see what they do and kind of learn ahead. It'd be really useful. And so what we do is set our address registers. If we look at A1, and as before we've got A1 pointing to I am copying some memory, which is the string, but this time we're going to move 2 bytes, and when I do that you'll see that the I and the space is being moved to the destination, but you'll notice that nothing has been added to A0. That's still pointing to 9DA, but A1 is actually pointing to 9F2, which on the focus side is actually here. So you'll see that 2 bytes have been added to the A1 address because it's a word size of a word that is being moved. As I mentioned, what you can do is use minus, and that's how you do that. You can even do that, and just, in fact what I'll do is I'll even be brave and do move dot long word, which is 4 bytes. Now this is going to move 1 word and then decrement everything by 4 bytes, the A1 and the A0. Okay, so look at A0 and let's have a look at A1. So I would expect when we see this copy, we should see the IAM come into this address here, and the A0 should be decremented by 4 bytes, so that should land at 9D6, and A1 should be 9E. 9EC, yes, and there you go. So 9D6, 9EC, and you'll see things have moved. And there you go. Okay. Right. So given that we've done that, what we can actually do now is actually copy a whole block of RAM, and the way you do that is with this bit of assembler here. So typically, as I mentioned, what you do quite common in a game is actually copy a block of RAM from one place in memory to another place. And typically what you do is you say, right, I've got a block of RAM that I want to move for whatever reason, and it's this size or it's of this kind of format, and it ends with this particular value, and I'm just going to copy it and move it to somewhere else. Happens all the time. So I've got a snapshot for this, and we're just going to take it each line by line. Snapshot and snapshot manager, and this one here. Beer's going down well tonight. Okay, so this should resemble the source code that I have in the slide, which it does, which is great. Now I'm just going to go down and talk about what is actually happening here. So the first thing is we're using a global label called maximum message size, and we're using a value here which is set by this directive, which is called EQU for equal, and we're setting the value to 100. So whenever there's any assembler references this max message size global label, it means set it to the value of 100. Now this is a constant value, it can't be changed, it's part of the assembler. It doesn't allocate any memory at all, it's just a way of referencing this, global label and this particular value, because typically if you have 1,000 lines of assembler, you might be setting the same value of 100. What happens if you want to change all of those values of 100 that you might have dotted around like 100 times or 200 times? Instead of having to go around every line of code looking for the value of 100, what you can do is just set it, just change this value here in the global label. That's the reason we do that. So what we're doing is we're starting the code and we're saying move a 32-bit value of 100 minus 1 into D7, into the data 7 register. And we've got some values, we've got some familiar instructions here: load effective address the source into A0 and load the effective address in the destination. And what we're going to be doing is we're going to copy this memory, will be copied, this string, and we're going to copy it into destination. Okay, now what we're going to do is we're going to copy the whole lot. However, if the string length, I apologize, exceeds the maximum message size, then it will stop at 100. So if the source string is, say, 200 bytes, it will only actually copy 100 bytes, because what you don't want to happen is what's called an overrun, and bad things happen then, and it's one of the the classic security issues that are often found. Buffer overflows, always found in programming languages. So we're just gonna look at that. So what we're going to do is we're going to just do a little loop here. If you remember, it's a little while loop, because we've got this decrement branch. And what we're going to do is we're going to move some bytes. So we're going to move source byte into destination, dereferenced. Now if it comes across that it is this zero, this null zero here, remember what the branch of equal does, because the zero flag will be set. So if it comes across this, when it moves it, it's going to jump to or branch to the exit. But if it isn't, it's just going to keep copying. And what the DBF D7 will do is it'll decrement D7 by 1. Remember, including the 0, hence that's the reason why we have the -1 there, because it includes 0. So it will decrement 100 times maximum, and then if it hasn't found the 0 by then, this null terminated 0, it will just drop out of the code. Pretty straightforward. So it's just going to copy, keep copying, but if it comes across this 0, it's going to jump out and exit. So let's give this a try. So let's see if it compiles. It does. And let's trace it in Monarm. Okay, so here we go. So we're going to set D7 to 63, which is 99. We're going to set A0 to our source and A1 to our destination block. So if we take a look at A1 and focus that, I want to just start tracing and move this block of RAM. As you can see, as I trace each one, you'll see in the destination block it is copying the RAM, or it's copying the string. Now you'll notice that it hasn't come across the 0 byte yet, but it is about to. So as you can see, in the source, the 0 byte is here, and it's currently pointing at the 45, which is the E, and we're going to process that one, and we're going to move the last one. Now when we move this next one here, which is the 0, notice that because it moved a 0, it set the 0 flag, and what branch if equal is going to do is it's going to say, alright, I'm going to check that 0 flag, and it's found that it's true, and it's jumped across. So now what you'll see is, you'll see that we've got an entire copy. Remember, this is what the destination looked like, I should say. So if we go and focus on source, we'll see that it says this memory will be copied, and you'll see right after that, and this is what destination looks like, dest. So just to be clear, this is source, which points to C369E6, and if we go to dest, that is C36A02, and you can see it is a carbon copy of the memory that we copied across. Now just to check that the max message size is working okay, you'll see this is around about 20 bytes. What I'm going to do is I'm just going to say the maximum message length can be 10 bytes. So it isn't going to get a copy, it isn't going to get to reach that 0 there, it's going to stop before then. So you'll see that, let's give this a try, you'll notice that D7 is decrementing by 1, and if we point to A1 and we look at the destination buffer, it's copying away and it's copying away, and D7 is now 0, it's decremented, but it's finished, it's stopped copying. So it never reached that 0 byte, but the maximum message length was exceeded, so it's dropped out of the program. Okay. Hopefully that made sense. I'm really hoping it did, because we're going to come on to something a bit more interesting now, which is classic game sprites. What I've done is I've took a classic game, which is R-Type, and we're going to look at how this game, this is just an example of how some sprites might be handled in this game, and we're going to look at what we've learned so far and how we might be able to come up with maybe what I call a handler to manage the sprites in this particular game. So what we're going to do is look at analysing these sprites here. And the first one what we've got, which we know about, which is this spaceship, and then we've got the orb as well, which is in R-Type, and then we've got 3 of these enemy bullets here, which I've labelled the enemy small bullet, and we've got this enemy's laser cannon, we'll call it enemy big bullet, I should say, and then we've got another enemy type here, of which there's 2 instances of this particular enemy, and then we've got another enemy type, which is this one here, and then we've got this large guy here, which I've just labelled enemy type 3, and I've got them labelled 0, 1, 2, 3, 4, 5, 6, all labelled down there. So this is the type number of each sprite. Pretty straightforward. So what we have here is we've got, if you imagine this particular game, it has a limitation that it can handle 10 sprites at a time. And typically that's what I did in Rygar. I said in Rygar, because I don't want the game slowing down all the time, I'm going to say, right, only 32 sprites can be displayed at any one time. So what we might do here is we might say, right, we've got 10 sprite slots for our type, and we're just going to initialize them, each slot, which is a byte, to -1, to say that it's just simply unused. It's not used. It's not used as a sprite. The game has just started. You've got the get ready message popped up in the game, and then what happens is the game progresses on. The sprites start to get allocated. So as the sprites start to come onto the screen, they start getting allocated into these sprite slots. So the player sprite here will be handled sprite handle 0. Okay, and its sprite type, which we went through in the previous slide, is 0. And similarly for the enemy, which has appeared on the game, that's been given sprite handle 1. And the little orb which appears after a certain amount of time, that is being assigned sprite handle 2, 3, 4, 5, 6, 7, 8, and so forth. So these are the different types of enemies, and you'll notice we've got multiples because that's sprite type 4, which has been allocated handle 1 and handle 5. And the game is progressing on, and we still haven't allocated all of our sprites. But what might happen is the game, one of the enemies is about to fire a bullet, and what the game, one way the game will do that is that in an assembler routine, which I've labelled as a method called add sprite, what it could do is it could say, okay, I'm going to allocate sprite type, the sprite type that's going to appear on the screen, into D0, and the value of that is likely going to be 2, because it's an enemy bullet which is going to be fired at the player. And when I want to make a sprite remove, I'm going to say whatever comes back, which is the handle that has been allocated, I want to remove it by supplying the sprite handle to remove. So just to go through that, the player's going through and the enemy's going to fire at the player. So sprite type number 2, which is this enemy bullet, has then been sent into D0, and the add sprite method is being called, which might do the blitting of the sprite or something like that, or any number of different things within the game. And the output of that has been to allocate sprite handle number 8. So that is what the value of D0 has came back. Now the game might store that value, this sprite handle, and do something with it. And generally, the sprite would typically move in a direction. It would be aimed at the player. The player's moved, but it keeps on going because it's a missile. It's kind of going straight off until it goes off the screen. Then it'll be removed again. And when it goes off the screen, typically, the remove sprite would be called, and the sprite handle will be supplied, which is number 8, to say, right, this sprite's no longer needed, I need to remove it, and it will be deallocated and set back to -1 for the game to reuse it again. Now because the game isn't kind of sequential like that, and the player, due to the player kind of moving and destroying different enemies, which is the whole point of the game, it's unpredictable, a person is unpredictable. These sprite handles here, which are assigned, could be, they'll change randomly depending on what the player does and what the enemies do. So it won't always get allocated in order like that, is my point. So what we're going to do is we're going to take a look at that as an example. Hopefully that has made sense. We're going to take a quick look at it as an example, and hopefully it'll fall into place for you. Got a shot as well, a snapshot, and we're just going to go to that. Okay, so here's the code that I've just talked about there. Now, as you'll see, it is a bit more in depth, but don't fear, because I'm going to talk you all the way through it. Now, what we're going to do is we're just going to go through this. The first thing that I've done, which you'll notice, we've said I've declared that there's a maximum number of sprites. Okay, so remember what I said about those allocating a maximum number of objects or a maximum number of sprites to be used in a game? That's what I've done there. So first of all, we're going to look at max sprites, and if we scroll down, we'll see that I've got a sprites global label here, and I've used the repeat max sprites, and I've set a byte to -1. So we're just going to have 12 repeated -1 bytes in there. Okay, cool. And if we look here as well, I've defined each sprite type. Got the player, the orb, the small bullet, big bullet, type 1, type 2, type 3, as we had in this slide here. As you can see, they all match. And what we're going to do is we're going to just come down, and this is what I'm kind of doing you know, if you imagine the game kind of moving, we're going to say, right, the player has started the game, so we're going to add the player type sprite as a subroutine. So we're going to call the add sprite method with the sprite type supplied in D0, as we mentioned down here. Sprite type in D0, call add sprite, and what returns is the sprite handle. Now what I'm doing is I'm saying, once we've called add sprite, we test the value of D0, but if add sprite is -1 or it's a minus value, then it failed to add the sprite. So then we need to go off and do something to say don't bother with displaying the sprite, or you know, something else, some other condition happens. Now why would it do that? Now the reason it would do that is because what if your maximum number of sprites had already been allocated? You can't add any more because you've only declared 10, or in the code 12 sprite slots. If all those are filled up, I can't add any more, so it has to return with an error condition, and we're going to look at that. So we've added the player, we've added the sprite orb, and we've added an enemy appearing in the game as well. Now remember what I said about what gets returned. So in the return value, D0 is the sprite handle, that comes back out from add sprite. Generally what you would want to do is you would want to save that value, that sprite handle value, somewhere, or do something with it for later use, because the player sprite's typically a special type of sprite, you know, given it's generally controlled by the player. So what we're going to do is just look at the add sprite method. And what I've done is I've commented the code here. Add sprite to the game. Inputs, D0 is the sprite type to allocate, and output is the sprite handle, or minus if it's a failure. And what we do, and we've covered this before, we set a counter which is 0 to in D6. We set the maximum number of sprites in D7, and that is just in case that all the sprites are filled. We get our source sprite slots in A0, and what the first thing that we do is we go in this loop and we say, right, is the sprite slot that I'm currently pointing at, is that free? Is it set to -1? If it is, then that sprite slot is free. It's free for use, so I can allocate it. So what it will do is it'll say branch shift minus allocate, and it will jump down here and say move the value of D0, which is the sprite type, into the value of A0. Now why am I saying -1? Well, I'm going to come on to that when I do the tracing. And what we're going to do is we're going to say the value of D6, which is the counter which is the sprite handle number, is going to get returned. So what we're going to do is we're just going to go through this. Now if the sprite is used, okay, so if sprite slot 0 is used and sprite slot 1 is used, it's going to continue on and go into this loop and keep going round into this entire loop here. Now D6 is the sprite handle number, which is being incremented by 1 each time. So what we're going to do is we're going to just do a compile and have a look at this. So here we go. We're just going to say, right, this is the player sprite, which is in D0. And what I'm going to do is I'm just going to shift this across if I can, just so you can see what's going on. No, you can't. Hold on. Maybe if I do that, and then maybe do that. Yeah, we might be able to get away with that. Okay. So, oops. So we've set. I'll just focus this window up here. So we're at this point in the code here, which is the player 0 into D0. And now we're going to call this add sprite method. And the way to do that is we do Control Z, and as you can see, it's gone, and we're now pointing into the add sprite. So if I just get the source code for that, which is here. And what we're going to do is we're just going to trace this. So we're going to set the sprite handle to 0 because it's starting at the front, and the maximum number of sprites, which we said was 12 minus, remember we need to take into account the 0, that should be 11. Okay, so if there's more than 12 of them, it's going to come back with a failure. So we set D7 to 11. We get our sprite slots in A0, and as you can see, those are there. And what we're going to do is with this test.b, we're just testing this byte, which is at C36828, and we're testing what's there, and as we can see, it's set to a minus, but we're also incrementing the value of A0 by 1 byte, which is 1. So you'll see that A0 is going to increment by 1. So it's gone to 29. BMI, it is, because it's minus, the minus flag set, and it's going to allocate it. So the value of D0 is now going to be put into here. And there you go. Because that is the sprite type for the player sprite. And the handle number is going to come back for be set into D0, which is 0 because it's the first byte. And there you go. So the sprite type has been set into slot 0, and I'm just going to show you what's happened here. So the sprite type of 0 has been set here into this slot, and the handle number has been returned in D0, which is here. So that's 0. So we're just going to come on to the next example. Okay. Now the next example, and we're just storing the value of D0. The next example, we're going to move sprite type 1, which in the example is the player orb. Okay. Probably not the best example, but we're just going to do the same thing. And just keep an eye on the sprite slots. And instead of tracing the add sprite method or function, I'm just going to get it to run by tracing over it. And as you can see, that is ran, and it came back with the handle of 1 as well. But next, when we continue on, we're going to move the sprite type of 4 into D0 this time, just to make it change. Now the sprite type of 4 is this enemy here, okay? And what's going to happen is if we move sprite type of 4, this time I'm going to go into it, and we've set sprites, which is the sprite slots, the start of them, into A0. We test the value of A0. Now what it's doing is it's saying, right, is the first slot free? No, it isn't. It's actually set. It's set to 0, which is the player sprite. So it's going to add 1 to D6, which is the handle. So it needs to go at the next handle. We're going to check again the next byte. Is that free? No, it's not, because that is set to the orb. The orb is actually in this slot here, and it's going to increment on. And you'll see the value of D6, which is the handle, is set. And now what it's going to do is, it's going to say, right, is the next slot free? Yes, it is, because the negative flag has been set there, because it's set to -1. So it's going to say, yeah, that one's free. Okay, I'm going to move that sprite type into that byte slot there. Now, remember when I mentioned about the -1? Because the value of A0 has been incremented, okay, you will see that it's actually incremented on and added the extra 1 when the instruction's been ran. So as you'll see, A0 is pointing to C36A2B. Now A2B is actually the slot after. So what we have to do is we have to tell it to place the byte in the byte before. So let me just try and give you an example of that. So what this instruction is going to do is we're going to say move byte D0 into -1 of A0. So what we should expect, -1 of A0 is going to be C36A2A, because A0 is pointing to C36A2B. So when I do, there you see, we get the sprite handle. So you'll now see that we have 3 slots assigned, which is the player, we have the orb, and we have one of the enemies in sprite handle 0, 1 and 2. And number 2 has been returned, and we test D0. Now what we're going to do is we're just going to come on to deallocating the sprites. So remember when I said there'll be an action in the game where the sprites get removed? Well, this is actually really simple, but it does involve another instruction. So in this remove sprite method, we've got the D0 is the sprite handle to remove. So that's all we put in as a parameter, and it doesn't output anything because there's nothing to actually output. So what we do is we've got the value of D0 set to sprite type 2, sorry, to handle number 2, I apologize. And we're just going to deallocate that. So what it's effectively going to do is that this player, well, this enemy orb here, sorry, there's an enemy currently in this sprite slot here, and perhaps the player's shot the sprite and it now needs to be removed from the game. So what we're going to do, we're going to get the value of the sprite slots in A0, and we're going to deallocate this by saying move -1, which is FF, into A0 but indexed by the value of D0. So what effectively it's going to do is it's going to say, right, A0 plus the value of D0, if that makes sense. So value of A0 is C36A28, and if we add 2 to that, which will be 2A, that's going to point to C36A2A which is 4, and that is certainly sprite handle 2. What we'll find is when we trace this, it will set it to -1, and sure enough, there you go. So that has been removed from the game because we've just deallocated it. And we come back, and that is it. Okay, hopefully that gave a bit of a very simplistic explanation of some object management in a game. And as I normally do at the end, if that blew your mind, and what the level of this episode has went up stratospherically like that compared to episodes number 1 and number 2, you can find me on these channels here, certainly on Discord, where I get to hang out around about 7-8 o'clock a night on a night time. We're on Facebook, and as I mentioned, we've got AmigaGameDev.com, where you'll find all the source code and videos to the tutorials, and you can post questions and things like that. But yeah, do drop by the Discord site. There's a really nice community building there now. We've got about 30 people actually registered on the Discord channels, and it seems that, you know, this thing's really beginning to grow quite well, and I'm really liking it. I'm really loving these tutorials. Episode number 4 is already underway. I've already started the slides for that, and we're going to be looking at actually allocating Amiga memory and loading files into the Amiga memory, and looking at ProPacker as well. And you know, hopefully you'll found this exciting and interesting. And if you like the video, please like it, subscribe, and follow the series, because I'm sure you'll learn something about how to make some Amiga games in the end. It's going to be a long series, you know, but I'm enjoying doing it, and you know, I'm committed to doing it, and it'll, you know, really excited. Okay guys, that's it for episode number 3, and I will see you on episode number 4.